Okay, great. So I want to welcome everybody to this webinar. Thanks so much for joining. So what we're going to be doing, let me share my screen or different share. So I promise you, I only have 2 slides. So this is not going to be one of those webinars with endless, slide presentations, but rather we're going to actually go live and hands-on into our software called Magnus and show real-world examples on how to use AI assistance in your projects. So I only have 2 slides just as a very short introduction. So let me bring that up here. So just to quickly introduce myself, my name is Hans Bouwmeester. I'm the COO for PrimisAI. We also have online Diana Kanda, and she is the marketing director for PrimisAI. So who are we as PrimisAI? Just in 1 slide with a very brief introduction. So as PrimisAI, we leverage large language model powered generative AI towards accelerating design and verification. So it's really about doing your design and verification faster in less time. But that's not the only thing. It's also about using the AI to find problems early on. And if you find problems early on, of course, you save time later, and also it can help the quality of your result. Now, as we do this, and this is where we distinguish ourselves from, for example, GitHub Copilot or ChatGPT, we are offering a private deployment. So our deployment, our enterprise solution enables our customers to keep their data private and secure. It runs in a private cloud setting. Also, we offer the ability to extend the AI assistant or to equip the AI assistant with a knowledge base, which is a database you can use to store proprietary company knowledge. And the AI assistant, the LLM, will now use that data as it prepares its responses. Now you can think, for example, using that database to store the coding style guidelines, such that the AI will generate code which complies to your requirements. You can also use it to store intellectual property. This can be intellectual property which your company licensed, or it can also be intellectual property which your company created in-house. So then the large language model, the software can use that intellectual property in its designs, which you ask it to create. You can also think about earlier code, because very often design, of course, builds on, on previous designs. You can think of product specifications. Well, there's many applications for this database. It's in AI world, it's often referred to as RAG, Retrieval Augmented Generation. And then lastly, we not only use the AI to just have a, call it an EDA chatbot, but we go much further than that. We're actually equipping the AI with tools, with EDA tools, such that the AI can such that we can automate workflows using the AI. You can think about, having the AI call the simulator, look at the results of the simulation, and immediately try to fix bugs and rerun the simulation. So here's what we're going to be showing in the webinar live. So we are using a RISC-V CPU to really show real-world examples how to get the most out of Magnus. Magnus is our tool, our software. And we do this by really going through a complete flow all the way from, starting with nothing, going through requirements analysis, architecture, microarchitecture, logic design, verification, unit testing, creating the test bench, and all the way to ending with running a hello world type of simulation, really showing that the CPU is functional. And the webinar, of course, is only 1 hour. I'll try and see if we can have some time at the end for Q&A. But it is I have a lot of content to share, so I'll see what I can do there. The webinar is 1 hour. To run through this flow, it's really showing we can do what I'm going to demo. I can do it in an afternoon or less. So it really shows the tremendous time savings which you can achieve leveraging Magnus as an AI assistant for doing this. And what I'm showing here also is that we're doing this, we're going through this flow using a team of AI agents. And an AI agent you can effectively see as a domain optimized AI assistant. So for example, we have an AI agent which is specifically configured to do system architecture, or one specifically for logic design or debug or unit tests. So we have these different AI agents we can leverage to do the work. And so I'll come back to that more later. So with that, as promised, we are going into the actual software. So I'm sharing my screen, where you can see that our software runs in VS Code. So this is, you're probably familiar, the VS Code IDE. You can see on the right side the file manager, editor window here, which is empty in this case. And on the left side, you can see that effectively it's a chat interface. So very similar to what pretty much now everybody's used to, right? ChatGPT or a Copilot. You can ask any question, and you'll get your response from the AI, from Magnus, or in this case actually RapidGPT. RapidGPT is the underlying technology, the underlying software which we built our solution on. And we can now ask any question. So you can see I already just said hi and I got a response. But of course, in this context, let's ask a question which is RISC-V related. So I'm asking for a register file for a RISC-V RV32I, which is the integer instruction set CPU. So a very simple question for some code we'd like to generate. So our software runs as a client-server configuration. So this question now went to the server for interpretation and giving the response. And you can see that RapidGPT has been configured to ask some refinement questions on what it is we actually want. So we answer those questions like, okay, we'd like to have two read ports, and one write port. And it's asking do we want to implement this in actual hardware? So in other words, should it be synthesizable? So we'll say make the code to be synthesizable. And what you'll see, of course, as the next step, as you probably would expect, is that we get the RTL code for, in this case, the register file. So we'll wait for it to give the response. So here's the register file. And you can see two reports, one report with the registers implemented and a description of, what it is we did. Now, you may be thinking like, okay, GitHub Copilot can do this, ChatGPT can do this. What's really different other than that, as I explained, we're running in a private cloud context, right? And well, you're right. Yes, GitHub Copilot can do this. But if you really think about this, we're doing a lot of things wrong here, if I'm honest. Would you ever in a real world go, based on a single sentence and, one follow-up answer, right? Generate code? I mean, would this be the right way to do a complete RISC-V processor? How long would these prompts become, right? And how capable would the large language model be to actually, do this? So that's one thing, right? We're in sort of a Q&A mode. It's like Googling. We ask a question, we get an answer, and that's it, right? Everything sort of vaporizes from there. So there's no what we call prompt reuse. We're not reusing any of the prompts for later use. So it's not stored. The conversation history is stored. So if I switch and I go back, we still have it. But there's a lot of things wrong. Another thing is we're not following any methodology here, right? We're going from question to RTL, which is unrealistic again, right? So where's the flow which we normally follow? Shouldn't we first create a specification because before we're gonna do RTL coding? Now, of course, I could ask here let's create a specification first, but that's a lot of typing. There's also no real prompt engineering here. You may be familiar that you get better responses from AI if you think about how you phrase the question. So long story short, we can do much better than this. And that's actually what I'm going to show in the next step, where we're going to load an AI agent called Magnus. So you'll see me do this now. And not only that, so Magnus you can see as an AI agent, which we have specifically configured to follow a workflow. So now we're going to go through this process. Before RTL coding, we're first going to do a functional specification. Which functionality do we want to implement? And then a microarchitecture specification. And while you can read for yourself, that's the flow we're going to go through. Now, also, we're going to do some more. This in itself is already some prompt engineering, because if you divide your problem, if you partition the complexity in steps, you'll get better responses. It's just like a human being. If you create a specification first, your RTL will, as a result, will be better because you took a stepwise approach. So in other words, we're doing prompt engineering here. Another thing we're doing here is the prompt reuse, in the sense that we now effectively have two prompts instead of one. We have one prompt here, and we have a prompt as we interact. You can see this in this way of working. This is our methodology prompt. This is the how. And here we're entering the what, the content. So now if we effectively ask the same question, except I won't do a register file because we already did a register file. I'll ask a question like, I need, and we'll stay in the RISC-V world, right? I need an ALU for a RISC-V CPU. Or actually, let's do an RV32 integer and multiplication CPU. So we're doing one block, the ALU, inside the RISC-V processor. Now, one thing also to note here is that I introduced myself, and you can see that it introduced itself as Magnus. So in other words, we have loaded this agent, and this agent is specifically configured to follow a workflow. And as a result, you can see that the agent responds in like, gather requirements is the next step, because we gave it a workflow and it tells you step by step how we're going to proceed through this workflow. So we're going to go step by step. What's nice here also is you can define your own workflow. There's also pre-configured workflows in the agent. You can also, if you want to, you can skip a step. You can modify a step. You can redo a step. So you can iterate until you're happy with the response, right? There's many things you can do here. Now, in this case, what I'll do is you can see it gave some feedback on the requirements. You can interact on that, right? In this case, I'm just saying like, well, let's proceed. And the way AI assistants work is that, it will fill in any blanks, right? So that is very powerful if you, for example, want to do rapid prototyping, right? You can just, have it make assumptions for you. If you don't want to make it to assumptions, then of course you should tell it. And what you'll see now, of course, is that we're not going to immediately get RTL. Because we don't want it to. We want it to first create a proper specification defining what we're gonna, implement. And you can see that we're getting the specification as a markdown file, which means it's nicely human readable. I'll show that in a second. And it summarizes, this is configured inside the AI agents. It has effectively a template of what you would like the documentation to look like. This can be user configured also if you have certain preferences there, but it gives the brief introduction, the module name, the summary of the requirements, the features which are implemented in this ALU, and then the interface description with inputs, outputs, descriptions, and a description of the detailed operation. And as I mentioned, what's nice now is this is a markdown file, which means that we can just use VS Code to view it here as a human readable file. So it's very nice. AI can help you very quickly create a specification. It can be a starting point. You can edit it, of course, by hand if you like, or you can ask the AI to edit it if you'd like to make certain modifications. Now with that, I'll go back to our demo. Now I could continue with the next step, but actually because every response, you get the concept here, of course, every response takes a little bit of time. I have a pre-recorded, pre-done conversation history here, which I'm showing now, where also we're going to go, make it one step more complex. So rather than doing a register file or an ALU, we're now actually going to do a full RISC-V processor. At the beginning, we're still going to keep it simple. I'll show in the next step how we're going to make it more complex, how we're going to add complexity. But what we're doing for now is we're going to say like, okay, I need a basic simple RISC-V. It's for an ASIC with the integer 32-bit instruction set. It's for bare metal applications. So for now, we don't need a memory management unit or interrupt support or exception support or configuration status registers. Well, you can read the rest, of course. I do not expect you to try and read all this, right? I'll highlight the most interesting parts. You can scan through and get a feeling for, the contents of the AI assistant or the AI agent in this respect and how you interact with it. So you can see it starts with step 1, just like before. It's iterating with us on the requirements. It asks a few questions. But what's interesting is this, is that we're having, and this is prompt engineering also, we're having the AI, the Magnus AI agent is configured to perform quality assurance. It means that it basically looks at its own response and it critiques itself and it basically highlights what it thinks are issues which may need to be addressed. Now note I say maybe because an LLM is like a human being. It makes mistakes, it has sort of opinions, and maybe you say like, well, you know, this item, it's not so important, or we'll deal with it later, or, you know, I don't want to bother. It doesn't matter, right? They're just suggestions. But what you'll find is that very often you'll say like, you know, whatever, right? Maybe it says here like, you know, area constraints information could guide design decisions. Well, you know, that's true, of course, but do I want to bother now? Maybe not, right? So I just ignore it. But sometimes you'll find that there are things in there which really trigger you like, hey, wait a minute, I didn't think about it. And then, of course, if you address them now rather than later, you are saving yourself time later on. So you get sort of this free assessment, this free opinion as you go through the process. Now we're interacting on the requirements and we get the functional specification similar to before. And now we're going down further in that we're going to the microarchitecture specification step. I'm saying like, let's use a single stage pipeline. We're keeping it very simple here. And I'm also specifying a preference for a design partitioning. You don't have to do that. I mean, obviously, this is a RISC-V processor. You wouldn't want it flat, right, in one big RTL file. That would not be a good idea. You need to manage the complexity, not only for the human being, but also for the AI agent. So in this case, I just expressed the preference that I'd like these you know, these are commonly chosen in CPU world, right? I'd like to have those submodules. And as we proceed further down, you can see that the microarchitecture specification effectively is a similar document to the functional specification, but it now focuses on how we're going to implement this thing. So it lists the submodules, and for each submodule, it gives a brief description of inputs and outputs and a description of the detailed operation. So what it should do. And because we're describing this here now, we can expect the RTL coding we're going to do in the next step to actually give better quality RTL code. Less likelihood of any issues, any bugs in the code. So we're going down and you can see next step RTL coding. So we're just proceeding through the flow. So here's the RTL code for the top level. You can see the different submodules being instantiated. And for each submodule individually now, step by step, we're creating the RTL code. So here's the decoder. Here's the execute, the ALU, if you will. Here's the write back unit. Here's the pipeline controller, or in general, the control unit. And here's the register file. So much more of a flow using methodology to get from nothing to our RTL code, which is also hierarchical RTL. Now, next, what we're doing is we're going to do verification planning. Also there, before you ask the AI assistant to create a test bench, it's good to first create a plan of what you would like that test bench to look like. So I highly recommend to always make that a two-step approach and not just immediately ask for the test bench, or to really iterate on the plan first before you create the test bench itself. So here's the verification plan. So you can see that it suggests the following verification strategy. It's pretty high level, so we'll come back to that in a second, in that it suggests that we do unit tests. Now we actually will follow on that later in the presentation. Then integration test, the full CPU memory interface, well, you can read for yourself. But actually, as the human being, we know better in the sense that there's nothing wrong with this test plan other than that I'd like to start simple. I could have asked that here also. I just said proceed. I could have said like, start with a sanity check. Because, we've now created a whole bunch of RTL. We have to assume there are bugs in there. So we want to make it as easy as possible for us to debug the RTL, and to do a very high level abstract test bench is probably not a good idea yet. So what you see is that I actually give it an instruction to keep it simple and to create a standalone self-checking test bench that does nothing more than perform a sanity check. It should just add 3 + 5. So we're just doing a very simple ALU operation and checking that the result is 8, not by writing it to memory, but actually just by probing the register file. So with this, consider it like a bring up, a sanity check. It should be as easy as possible to get a first sign of life out of CPU. I'm also asking to help debug to have a plethora of display probes in the test bench, such that we can, make it easy if the test fails to find out what the reason is. And this will not only help the human being for debug, right, but also the LLM. So I'm actually giving it also some instruction like, I'd like to see which instruction is fetched, the decode details after the decoder, the ALU port values to see that indeed 3 and 5 are fed into the ALU, right? The write-back values, well, you can read for yourself. So long story short, here's our test bench. It instantiates the CPU. It gives a bunch of clocks. We actually also asked it to add a timeout mechanism. So you can see that here, just to make sure that it times out if the test runs away. It resets the CPU. It applies a couple of clock cycles. And here you can see that it took the add immediate for taking 3, adding 5, and these are the encoded instruction values. We give it a couple more clocks, and then we probe the register file to see if it works. And you can see that we have a number of probes inside the hierarchy to enable us to see what's going on. So the AI agent said like, let's report the cycle, the program counter. Of course, you can interact on this if you have your own ideas. But in this case, I just went with what the LLM suggests. Also, you can see that it gives the how to run the simulation, because you can see here in step 7, I asked it like, give me the iverilog command needed to run a simulation. Can be any simulator, doesn't have to be iverilog, just happen to be using iverilog here. Open source, easy, cheap, anybody can do it. So we're running the simulation, and in the terminal window, and you can see here, I pasted the outputs. You can see here that it doesn't work. As we discussed, LLMs do make mistakes like human beings. But what's interesting is, like human beings, LLMs are also very often able to fix their own mistakes. So they can help you debug the issue. And very often the easiest way to just, is to just take the simulation output or whatever tool output you're dealing with and copy and paste it into the prompt. So in this case, I just copied and pasted this, and effectively, just asking the agent like, well, there's something is wrong, help me debug it. I didn't even explicitly state that here, I could have, but that in a way is inferred. So it sees that there's errors in the code, and it analyzes and sees that there's a variable or a wire called PC, which actually should be declared to be a register. So that's a very easy fix, of course. And it also notices that some of the other errors are related to signals not being accessible in the hierarchy. So these probes here needed to be fixed for the right instance names. So I make those fixes and I run it again and it compiles okay. So we're one step further. And then I run the simulation. But you can see that actually, well, you can see here the result of the simulation and it fails. So you can see here, of course, these are the display statements in the test bench. And if I go down, you can see that the test failed. So obviously we have some more debug to do. Something is not right. And now I'd like to point out one important aspect as you're working with LLMs, because there is some techniques to get the best out of AI assistants. And one thing to notice is that we now have this complete conversation history. So it's a very long conversation. And you have to realize that every question which is asked from the AI takes every, prior discussion into account. And as a result, you're starting to, in a way, overload the large language model. And as a result of that, the accuracy of the responses can go down. And because now we're making it a little bit more complex in that we're going to debug something, you have to ask yourself at any time, maybe it's a good idea to start fresh, to start a new conversation. And because debugging is complex, that's actually what we're going to do. And you can see here in this file, this prompt file, I started a new conversation specifically to debug this issue. Now, of course, because it's a fresh conversation, we need to prime the LLM with the relevant information it needs to debug the issue. And for that, we have the capability to load files. I already showed that earlier as I loaded an agent. But you can also load here earlier files which you have created. So in this case, I loaded it with the specifications and the individual Verilog files which together constitute the processor. And now that we have the context set, right, I'm doing effectively the same as before in that I copied and pasted the simulation output, but also I'm adding some more prompt engineering. You may be familiar with the concept of chain of thought reasoning, which basically means that you ask the large language model to think step by step, to analyze it step by step. And by doing that, you get a longer response, but you also get, as a result, likely a more accurate response. So what I'm doing here is explicitly asking it to think step by step as the LLM debugs it. And, as we now go down, the test failed, of course, as we had said earlier. You can see now that it goes step by step through the simulation results, and it tries to analyze why it fails. So it sees that the program counter started at 0, which is correct, of course. And it also says the first instructions is all zeros, which is not expected because we expect the add immediate. Now, being a human being, LLMs sometimes get it wrong. Well, it does say it might indicate an issue with the instruction memory initialization. But, it's clear that we are in cycle 0. This is probably still just the reset value. So I'm not immediately worried as I read this. And you can see indeed in the next analysis, next cycle, it sees that we're correctly fetching the instruction as expected, which is add immediate. And it sees that the decoding happens correctly, but it also sees that the ALU result goes to access. So it looks like there may be some issue inside the ALU. Now, I won't read everything, you can scan through it, right? but it basically infers that, you know, something may be wrong with the ALU, and it suggests to resolve it, to review the ALU, focus on add immediate, and it has some more suggestions here. Now, rather than me doing it, I actually bounce the ball back to the agent, just asking it like, well, you know, you look at your own stuff or your own analysis, double check it and propose a fix. You can see that it, you know, it double checks its analysis, and long story short, it proposes an additional case in the ALU for supporting the add immediate instruction, where there was an issue there. So we make the changes proposed, we run the simulation again, and you can see now indeed that it passed. So you can see how, you know, together with the LLM, we debugged this issue. Just by basically feeding the results of the tool back into the AI agent. Now, not everything is okay yet. You may notice that there's access here that doesn't seem right. Why does it work? Well, they are on the memory interface. So, you know, are there more bugs in here? Oh, yes, there are. We haven't found them yet. But at least, you know, the first sanity check now works. And I'll show you actually to bring it to the next level in the next part of the presentation. So with that, we're going to actually go one level deeper. One thing to notice is that, as I explained here, we're going through a workflow, which is great. But also because we're going beginning to end in one prompt, we ended up with a very long conversation history. And as a result, yeah, the accuracy of the large language model just goes down as the conversation goes deeper. So how can we take it to the next step and actually go more complex, do a next level, more complex processor with more features, and also solving this problem? Well, the way is simple, of course. It's just about, you know, managing the complexity by going step by step and effectively taking each of these steps and dividing them into sub-steps. And the way we're doing that, and you see this here on the right side, so you can see that I have a number of prompts here, which I numbered in sequence, and every prompt here is a step in the flow. So you can see that we're now going to do a more complex CPU, starting with the functional specification, and go through all these steps one by one. Also, I'm taking a little bit of a different approach in that I'm putting the requirements, rather than in the prompt, I'm putting them in the file here, such that it's reusable. And I'm actually loading dedicated agents. So rather than using Magnus, I'm actually now loading, you can see it reported here, I'm loading the architect AI agent. So that is an agent which is specifically configured for doing architecture creation. Now, other than that, it's very similar. So we're gathering the requirements, and we're also getting the relevant information from RAG. We haven't really spoken about that, but this is the knowledge base, the database I spoke about earlier. And as we go down, I'm asking it to write the specification, and the specification we get is very similar to before, except it's longer because it's a more complex CPU, because we're now actually implementing exception handling support and interrupt requests, and a small set of configuration status registers. So it is a more complex CPU again. Now, one thing which is different or new now is that as we're writing the specification, why shouldn't we, just like a human being, before we proceed, explicitly review the specification and critique the specification to see if we can improve it? And that's actually what we're doing here. So we now have a separate step where we use the AI, we use Magnus to look at our result. And this is, in my opinion, a very powerful application of AI. You have this additional set of eyes, which is sort of free. You can ask its opinion, right? And also you can ask it to focus on certain things as you review it. Now, in this case, what we're doing is we're just asking, you can also see that we loaded a dedicated agent again, a review agent. And you can see that we're just asking it to, look for the documents and look for instruction set encodings, interrupt, exception support, and, and do a review in that regards. So we keep it at a fairly high level. It identifies the RAG documents like before, but what's more important, more interesting is this is our review. And you can see that the agent has been configured to report the review not as a big blob of text, which you often see LLMs do, right? And you really have to look for, what's important. But it's nicely structured in that it reports, what it considers high important items and medium and low. It also gives an executive summary, and it actually does a QA assessment like before. You can see that it suggests the exception handling description could be improved, and also the details on the configuration status registers. Now, of course, it's good to do this before we proceed with RTL coding. It gives here the recommendations you can see. So what I'm saying is okay, why don't you follow your own recommendations? It also had a suggestion to add timing diagrams. I'm saying it to not do that, simply because LLMs are, today at least, not that good at doing diagrams yet. So I just tell it well, don't do that, just do recommendation 1 through 5. And as a result, we get the updated specification with now a more elaborate, for example, here for the configuration status registers, a more elaborate description of what we require. So that is the review for specifications. We do the same for microarchitecture specification. I won't show that because it's just very similar. But after RTL coding, which is similar to before, it's a hierarchical RTL, of course. But after RTL coding, now we're actually also doing a code review. And again, this is where AI, in my opinion, can add a lot of value, because you can focus your review on certain things. And, some things may not be interesting, but there may be interesting things in there where you can find bugs before you start actually doing simulations. So you can see we're loading the reviewer agent, and we're loading the relevant information, which are the specifications. And in this case, we're doing unit by unit a review, a code review. So I'm using the execute unit. I don't load any other RTL because it's not relevant here, right? We're going through a workflow now, which is dedicated to this review. And we're actually doing different types of review. The first review we're going to do is just for coding style. So we're just looking at the, does it meet the coding style guidelines? And then we're going to do a logic functionality review, really seeing if we can find logic bugs. And we're then doing an overall type of quality review. So we split it up in 3, separate reviews. And the first one is the coding style. And you can see here actually that we provided it, and this is what we included in the RAG database. The coding style guidelines we wanted the code to adhere to. So we're going to check whether indeed the RTL code produced meets these requirements. And of course, you can create your own. This is just the example which we use. So going down, you can see that it, in a nicely, again, human readable format, it checks off the different items. and gives its own opinion on whether we met or not those items. You can see here we get a diamond, and that's actually because, oh, that means it's not applicable, right? In this case, it's not applicable because it's not sequential logic. This is just the execute unit here is just combinational. So you can see none of the test actually fails in this case. And then it proposes updates. So it proposes some updates, but I ignore those and just proceed to the next step. Now, next step, as we discussed, is we're going to do logic functionality review. And what's interesting now is this one here. So here you can actually see that it found, as it reviewed the code, that there's a discrepancy between the specification and the implementation, in that the implementation does not handle the jump and link register instruction. So this, of course, is a great example where the AI helped us to find an issue early on, thereby saving time later and potentially also getting better quality in the end. Because, of course, this is a very important instruction. We need to support this, and I want to fix this now rather than later. So it proposes a fix. You can see here, add jump and link register handling, and it proposes a fix to the execute unit in order to properly support that. And then last, we're doing an overall design quality review, which means we configured the agent to look at more, call it intangible things like, how area efficient are we? What's the performance, the power efficiency, testability, extendability, etc., etc. So that's the next value add, which I think is really, really high for AIs to assist with code reviews. Now, next we're compiling the RTL, just like before. You can see that we just follow a little workflow. We're debugging some issues in the RTL, but I'm not really showing what or here because it's very similar to before. But this is actually new. What we didn't do before, and which is another very high value add for AI, is to do unit testing. And unit testing in my past is something where I remember, I've been part of different design teams, and we would always, over lunch or in meetings, we would always tell each other like, yeah, we should do more unit testing because then we can find the bugs at a lower abstraction level, right? And, we find them earlier, we get better coverage. Well, there's a lot of things to be said for doing unit testing, of course. But doing unit testing is often a pain because it requires you to write a test bench which is dedicated at a low abstraction level. For example, if you would do one for a decoder in a RISC-V CPU, you have to think in terms of the encoded and decoded instructions and drive the ports accordingly. So long story short, we never really did much. We had a few units where we did unit testing, but not that much. But on the other hand, the AI is, it's very good job to give to AI because it is managed complexity. You're at the submodule level, right? So why not ask the AI to write a test bench and to simulate it and debug it? And that's what we're doing here. We have a dedicated unit tester AI agent, which I'm loading here. In this example, I'm showing we're doing this submodule for submodule, of course, because we're doing unit testing. So we're doing a verification dedicated to the exception unit in this case. And for that, we need to show it the top level because it fits in there and the specifications. We don't have to show it anything else. And then it does the test planning before we create the test bench. So you can see here, we ask it to create 3 tests, and you can see here a nice description of the different tests. So this is for the first test. We want to test, or it suggests we test the instruction address misaligned exception. And again, doing this as a human being, it's just a pain. I like the AI to do it for me. As you can tell, I'm convinced myself. So we're proceeding with creating the test bench, similar to before, but actually this unit tester AI agent has been configured to create a test bench using a template. And what's nice of doing that is that, you know, if you don't do that, every time you ask an AI assistant for a test bench, like GitHub Copilot, you'll get a different implementation. And then as the human being, as you read the test bench, you have to relearn because things are in different locations, etc., etc. And here, every time you generate a unit test level test bench, it'll look effectively the same. It uses this template. And this template actually has been configured. You can see that it defines a task for each of the tests, such that, you know, this is really the content for test 1. And everything else in the test bench is separately mentioned. And here, this is templated, so we're executing the test. And the way we actually do it is that we run a test and we first run it in normal mode. So debug mode is 0. And if it fails, then we turn on debug mode and we get the simulation log, which is a nice way such that you don't always get all these display statements over on your screen. Well, long story short, so this is the unit test. And of course, now it's very similar to before in that, you know, some of the test passes. The first one immediately passed, the second one failed, and we're debugging it like I showed before, right? So we're analyzing the issue. Now we can see the second test passed, but the third one still failed. We're interacting with it until we have all 3 tests pass. So again, unit testing is really an area of a very high value add for AI. Now, next we're proceeding down. I see I have 8 minutes, which should work. So we're proceeding down the next step in that we're generating a test bench. I'm doing this in a stepwise approach. You can see here that the instruction here I give it that it needs to instantiate a module called mem-model. And I'm doing top-down, which means that this mem-model, I should say, is empty for now. And, you know, going through this, you can see that here's our test bench. And you can see that it instantiates a memory model. And this is the memory model which we're going to use to load our assembly code into the CPU to execute. Because, of course, we're going to use the memory interface properly now. We're not going to do what we did before, is just the probing. So here we're actually coding the memory model. So, you know, you can just see here, there's a lot of stuff in here, but I'll point out what's interesting. You can see here that actually this is where we're reading a file which contains the hexadecimal or the binary for the compiled assembly code. Then next what we're doing is we're using Magnus, because it's important. Magnus, of course, is language agnostic. You can use it to generate assembly tests just as well as you can use it to do Verilog coding. You can also use it to create Python scripts or, you know, analyze MATLAB code, for example, right? So in this case, we're using it for creating a first test. It's a bring-up test, so we keep it very simple. We're just adding 2 integers and checking the result. Now, I didn't like the response first time because it uses eBreak instruction. That is supported because as per the specification, we're now supporting exceptions and interrupts. But I thought like, well, you know, let's just keep it simple at first. So I'm interacting on the implementation of the test by asking it like, you know, add a pass label and a fail label, which it did. But it still used the eBreak inside pass because I wanted also the test to be self-checking, right? But it still used the break instruction. I didn't like that, so I'm actually saying like, let's not use eBreak and just have pass and fail jump to themselves. And then in the test bench, I modified the test bench such that it detects whether the program counter becomes equal to the pass label or the fail label. And if so, it reports, of course, the result of the test. And you can see now that we have the assembly the way I liked it, in that it, if it passes, it just keeps cycling here. And if it fails, it keeps cycling. And it's a self-checking test. Now, next what I'm doing actually is I'm instrumenting the test bench. I'm adding something which is I wanted the test bench to write out a trace log file, which is common in CPU world, in that you would like every cycle to see the state update to the processor. So really what happens to the register file. And you can see in the instruction here that I'm adding some code to the test bench to specifically every cycle, report the write backs and the memory read and writes. And well, here's the updated test bench with the trace log writing. Next, what I'm doing, I'm actually running Hello World. And in the interest of time, I just go very fast. I go through, I think, a little bit of debug, but you can see I get it to pass. You can see also here's the response of the tracelog file. You can see the program counter, the instruction, and the update. In this case, register 1 gets the value of A, which is 10, of course. Register 2 becomes 19, which is 25. So, I get the very basic sanity check to work, but it is assembly code now. It's different from before. But that actually got me thinking as I went through the process here. I thought wouldn't it be nice if the test bench, rather than the encoded instruction, could show the decoded mnemonic, the actual assembly instruction. So I thought well, why not, this is another nice example of AI. It shows this is a pain to do as a human being. Why don't we write a disassembler? And it's just a function such that we can use it. We can call it from the test bench. We call it disassemble. And it takes a 32-bit encoded instruction and it outputs a string which represents the disassembled instruction. And, long story short, here's the function it created. And can you do this as a human being? Oh yeah, of course. It's actually easy to do this because it's just a case statement. But it's a pain to do this as a human being because you have to really dissect the instruction, where do all these bits sit and what do they mean, right? So this is a very good example where maybe it's not that complex, but you can save a lot of time using AI for this. Now, long story short, I, of course, equipped the test bench with this disassembly capability. And I'm going to run now live the iVerilog compilation. So you can see we're compiling the RTL code here. We're adding the test bench, the memory model, and the disassembly function. And next, we're going to first run the simulation with the very small self-check hexadecimal code, which I compiled from the assembler. And you can see here that it nicely reports every cycle, the program counter, the instruction, which was fetched from that address, but also the disassembled instruction and the state update, right? So you can see what happens in the register file. Now, similarly, I created a more complex test where I'm doing arithmetic testing. So here's a test. This is, by the way, a very nice also for the AI. It's really great to use AI for doing constrained random test generation. So in this case, I asked it, I like an assembly program which tests the arithmetic capabilities. So you can see it uses adds, subtracts, logic operations, shift operations, but nothing else. So we're really focusing the test. It's random, but focused on a specific area. And you can again see, of course, the state update to the register. Now, next what I did is, load store. Does the memory interaction work? And I'm showing that here. So I did a simple test, focusing on load stores. And you can see that now we're also updating or reporting the memory reads and writes. Now with that, I see we're pretty much on time, 1 minute over. Hope you forgive me. I hope that I've been able to show how, how AI, if you manage it correctly, and our software Magnus configured with AI agents can really help save tremendous time as you are, basically using the AI as your assistant, as you're, as you're designing something. Now with that, I've reached the end of the webinar. I apologize. We're essentially out of time for Q&A. But I would highly encourage anybody who has any questions to drop me an email. I think the email, Diana, maybe you can confirm. I think my contact is in the flyer which we send out, or otherwise maybe you can put it in the chat. So I highly encourage anybody who has any questions to reach out to me through email. I'd love to, of course, with your company, if you're interested, to do more of a deep dive and tell, and explain what we can do to add value to your company specifically. And with that, I think, I want to thank everybody, of course, for attending. And we've reached the end of the webinar.